Okay, I want to talk to you about Newton's third law. This is the third and final one that we're going to talk about. And it goes basically like this. For every action, there's an equal and opposite reaction. So action, reaction. It also, another way sometimes is put, is forces come in pairs, right? For every force, there's got to be another force. And this is not two forces acting on the same object. These forces act on different objects. For example, if I push on the wall pushes back on me with an equal and opposite force. So for example, I push on, let's say not the wall, but let's say that I push on a block. With 500 newtons of force. That's a lot of force, by the way, but let's make it 50. So if I push on a block with 50 newtons of force, that means the block pushes back with 50 newtons of force. So if you are looking at a problem and you figure out that it's a Newton's third law problem, it's usually pretty easy because whatever the applied force is going to be the force that's applied backwards in the opposite direction. If I imagine this is me, and this is the block, let's say I'm 60 kilograms and the block is 6 kilograms, right? And I want to draw free body diagrams for this. You know, maybe both objects have gravity down and a normal force up. Now I'm pushing the block to the right, so I am applying a force of 50 newtons. And the block, therefore, is applying a force back on me of 50 newtons in the opposite direction. Now, if we think about this in terms of Newton's third law, we know that the total of all these forces is your net force. And in this case, the block is not accelerating off the table. It's going to stay on the tabletop. So this weight and the normal force exactly cancel each other out. Similarly, this weight and this normal force cancel each other out. So both objects have a net force of 50 newtons. This one was to the right. The net force on you, I'm going to put a negative in here, is to the left. So in equal and opposite directions. Now, just because they have the same force does not mean that they have the same acceleration. So let's think about this. Acceleration on the block is net force divided by mass, or 50 kilograms divided by 50 newtons divided by 6 kilograms. So 50 divided by 6 ends up being 8.33. And the acceleration on you is also the net force divided by the mass, also 50 newtons. But you are much, much more massive, 60 kilograms. So instead of 8.33 meters a second, I don't even need a calculator for this, but I'm doing it anyway, because it should just be with a decimal point twice, 0.833 meters per second squared. So the forces are equal and opposite, but the accelerations are not. They're opposite directions, but definitely not opposite in magnitude. This is true also for gravitational forces. Like if I drop this pen, right, the pen falls towards the Earth actually falls towards the pen too. The Earth is pulled on by the pen by the same amount of force that the pen pulls on the Earth. Now the difference is that the Earth is very, very massive. So the acceleration of the pen is fairly big. It should be 9.8 meters per second squared downward. But the acceleration of the Earth, because the Earth is so massive, is going to be a very, very tiny number, almost impossible to measure. But we can see with stars and planets, for example, that the sun, we know that the sun pulls on the Earth. The Earth actually does pull on the sun a little bit, and you can measure this sometimes with stars. Not a lot, but just a little bit, enough that you can measure. So thank you very much for watching Newton's third law.